Hello, welcome to our project video. My name is Andrea Torres and I am the Systems Engineer and Project Lead of Team 25019. Today, we're going to be presenting the Small Autonomous Amphibious Delivery System. But before I get into any details, I'd like to introduce the rest of the team.
Hello, I'm Miguel Ayala, and I'm one of the mechanical engineers in this team.
Hi, I'm Devin Agarwal, and I'm the second mechanical engineer on this team.
Hi, my name is Raymond Robles, and I'm one of the electrical engineers on the team.
Hi, I'm Andrew Smith, and I'm the second electrical and computer engineer on this team.
Hi, my name is Griffith Wheely, and I'm one of the software engineers on this team.
Hello, my name is Caleb Chang, and I'm the online software engineer on the project.
Imagine that you're a first responder helping a city in the aftermath of a hurricane. Streets are flooded, power lines are down, and debris is everywhere. As you drive through the chaos, you spot a male victim across a flooded area yelling for help. You quickly realize he's having an asthma attack. You have the inhaler, but getting it to him is dangerous. In critical moments like this, there's often no safe or efficient way to deliver small items across dangerous and inaccessible areas. That's why Raytheon challenged us to develop a small delivery system that can move across both land and water, empowering anyone to respond quickly when every second counts.
The Small Autonomous Amphibious Delivery System is a Phase 1 project that features a durable hull for housing electronics and payloads, 2 water thrusters for propulsion, and 6 wheels to move it on land. It also is equipped with a LiDAR, a magnetometer, GPS, LED lights, and a live streaming camera to enable accurate routing and real-time obstacle avoidance. A Raspberry Pi 5 manages data processing from sensors, while an Arduino handles inputs from electronic speed controllers to operate the thruster and the wheel motors. Users control the system through a graphical user interface accessible on a tablet, smartphone, or computer.
Now that we've seen our finalized product along with its features, let's take a moment to rewind and walk through how we actually got here. Step 1 of our design process was all about understanding the full project scope. This involved identifying the core problem our product is intended to solve, and most importantly, understanding what our customer expects in our final delivery. After several meetings, in-depth discussions, and a mission matrix provided by our customer, Raytheon, we were able to define a clear set of functional requirements that shaped our system's direction.
Furthermore, these functional requirements helped us determine the necessary components and how each one needed to work together to meet those requirements. This understanding guided the development of our system block diagram, which outlines the interaction between all major subsystems.
So step 2 focused on the physical design phase, which included brainstorming concepts and conducting trade analysis. The design was centered around a strong foam bolt hole donated by Hydronaulics. To determine the most effective land mobility solution, we conducted a trade study comparing several different mechanisms such as tank treads or four-wheel drive and others. And after thorough research and feedback from our sponsors and engineers, we decided on a 6-wheel configuration with 4 of the wheels being actively driven.
Step 3 involved prototyping and subsystem testing as we gradually built up to our final product. Our minimum viable product, or MVP for short, 1 and 2 focused on integrating all components required for water navigation and manual control. We began by individually testing the thrusters, which were then mounted onto the boat. In parallel, we developed a user-friendly GUI that allowed control of the thrusters from a smartphone, tablet, or computer. Once both the software and the hardware were ready, we integrated the two and conducted a test at the Silver Bell Lake here in Tucson. We conducted this test to verify the system's functionality and ensure it could navigate while carrying a payload.
Continuation in parallel with the water navigation developed, we worked on a prototype to validate the functionality of the drive chain.
To do this, we built a small RC car using 3D printed parts, including the frame, motor mounts, and the wheel supports. This prototype served as a proof of concept and helped demonstrate that our drivetrain design would work as intended.
After verifying the functionality of the RC prototype, we moved
forward with integrating the drivetrain mechanism into a full system. To do this, we initially used 3D printed parts for the assembly and gauged the dimensions of the components for the full-scale design. Once we finalized the correct tolerances, we transitioned into manufacturing the components out of metal for improved durability and performance, which allowed us to perform subsystem level testing.
With the newly assembled system, we successfully demonstrated that our product could float and navigate through water while carrying the full wheel assembly, onboard electronics, and payload. However, when it came to land testing, the results didn't match the success we saw with our RC prototype. The full-scale system faced challenges that hadn't been noticeable in the smaller version. Specifically, the motors we were using and the torque output was overcoming the clamping force of the coupler that connects the motor shaft to the axle. To solve this issue, we moved the motors to the top of the frame and added a gear reduction. This takes the high rotational speed of the motor and translates it into a lower rotational speed at the wheels. After testing, we found that the system behaves as intended and allows us to begin verifying our land-based requirements.
Despite the issues we encountered during our design process, we were still able to verify multiple system requirements regarding our critical functionality, which is both the land and water navigation. With our most recent water navigation test, we successfully verified 15 out of 54 system requirements. These requirements cover basic water navigation functionalities, including navigating over submerged objects and more. Moving forward, we were able to verify 5 requirements related to our land navigation assembly. Next, we verified several requirements related to our graphical user interface. Testing confirmed that the GUI can send notification when the battery level drops below 60% and meet other key requirements such as displaying the current coordinates of the system. In summary, we have verified a total of 44 out of 54 system requirements. This leaves 12 requirements still pending verification by senior design day.
Okay, so over the course of the project, we had many challenges. One being that we kept frying Raspberry Pis, and then the other one was that we were frying our magnetometer and our GPS. So we found out on our magnetometer that we had the wrong data sheets given. So one of the things that we had to learn was we had to get our data sheet straight from the manufacturer and not from an online source, because one of the sources said it was 3.3 volts and the other one was 5 volts. We chose 5 volts and we kept frying magnetometers. We were given a budget of $4,500 to develop our product. As of right now, we have spent a total of $2,700. $520 were used to buy replacement components. Considering this, our remaining balance is $1,400.
Overall, the main functionalities of the system have been successfully verified. While a few requirements remain to be fully validated, we are confident that all critical functions will be operating effectively by senior design day.